Let's look now at how to compute the integral of a slightly more involved function. Again, this is very easy, but I want you just to focus on all of the rules and all the processes that we're using in order to compute an antiderivative for that function. So first of all, we're going to use the addition rule. Remember, if we're taking the antiderivative of a sum or a difference, which of course is the same thing as a sum, we can split it into the antiderivatives of the two terms. Now notice that every time I split an integral into two integrals, the dx has to be attached to each of the two integrands. Remember that dx is not there just for show, it plays an important part. Now what we're going to do is for the first integral, well, that's the integral of a constant. We can use the linear rule, and it tells us that that first integral is just 5x. And now you must say, well, where is the plus c? Well, notice I still have another integral to compute, so there is a constant in there as well. And there is no discontinuity here, so I can just combine those two constants and just deal with a single one. What about the second integral? You may have already figured out what the antiderivative of that is, but let's pretend the numbers were not as easy, okay? And so let's use first of all the coefficient rule. We can actually take that 4 out of the integral. That leaves us just with the integral of x cubed. Well, now that's an integral to which we can apply the power rule. And so remember, how does that work? Increase the exponent by 1 and divide by the new exponent. Okay, and now this is the step where we need to add the plus c, because now we're done with integration. So we need to add the fact that there may be a plus another constant. Now at this point, I know that you're going to be very anxious to get rid of those two 4's. Fine, you beautify to your heart's content if you have to. And so we can write that the antiderivative of that function is 5x minus x to the fourth plus c. Okay, but remember, this last step is not required. It may be useful if we have to do something else with that antiderivative, but it's not a requirement of computing it. Here is another simple example of an antiderivative that we can use to demonstrate a few little techniques, simple basic techniques. Now, first of all, notice that we're trying to integrate a quotient. Well, we know that there is a quotient rule for derivatives, but we also remember that the quotient rule for derivatives is not that easy, and in fact gives us a fairly messy formula, and unraveling that one by starting from that formula and getting an integration formula turns out to be so complicated it's not worth doing. Besides, you may remember that the quotient rule can be obtained by combining product and chain rule, and both the product and the chain rule give rise to two methods of integration, so we're going to use those two. But in this case, things are a lot simpler because, first of all, I can rearrange that integrand. So what I can do is I can split that integral, taking advantage of the fact that the denominator is a single power of x, and write it as a sum of 3 fractional powers of x. Notice that I'm putting brackets around that sum. Again, those brackets are not optional. You have to put them there. Remember that dx went into that position by eliminating a denominator. That dx is multiplied by the integrand. And so if I don't put those brackets, it turns out that dx will multiply only the last term. Not what I want. So keep always the brackets around the integrand if the integrand consists of a sum. Okay, so at this point, what I can do is I can use the addition and the power rule. So I can split that integral into the sum of 3 integrals and apply the power rule to each of them, since the exponent is never -1. And so if I'll leave it up to you to check that this is what you end up with. By the way, if you're still a bit uncomfortable with fractions, well, practice a bit, because we're going to be using fractional exponents quite a bit. So we're done, right? Well, not quite. What's missing? Yes, the plus c. Okay, never forget that one. We have done the integration, so we need to add the plus c as the end. Again, this looks a little bit ugly. If you want, you can beautify it, and you may want to check that in fact what you end up with is this particular form. You may also beautify it further by changing those half powers to square roots. That's fine with me. If you want to spend the next 45 minutes doing that, go ahead, but probably you may want to do some more examples of integration to better your skills. So once again, these are some really basic examples. Do some more of the same kind of level of difficulty, and then in the next few classes we're going to look at more techniques for integrating more complicated functions.